What if we could take one of the most destructive forces in the entire universe, the very thing that fries our satellites and puts astronauts at risk, and actually turn it into a power source? Well, it turns out a recent discovery might have done just that, completely flipping the script on how we think about radiation.
I mean, think about it. For literally as long as we've been sending technology into space, this has been the undisputed truth. Radiation was the bad guy. It was this constant, invisible threat that we had to shield against, no matter the cost. It was just rule number one in engineering.
And for good reason, right? Before we can really appreciate this massive breakthrough, we have to get a handle on just how devastating this enemy really is.
So, when one of these high-energy particles slams into a microchip, it just wreaks havoc. It can flip bits of data, a 1 becomes a 0, and corrupt software in a flash. Over time, the total dose wears down the components, leading to this slow, inevitable death. And even worse, it can physically knock atoms out of their place in the crystal lattice, causing permanent, irreversible damage to the hardware itself. It's not pretty. For decades, the only thing we could do was play defense. We'd build thicker shields, we'd write smarter error-correcting code. But what if that whole idea was just wrong? What if, instead of building walls to block a storm, we could build a windmill to harness its power? And that's the core of this whole revolution, changing our mindset from hazard to harvest.
And listen, this isn't some far-off science fiction plot. In 2026, a very real discovery came along that completely changed everything we thought we knew about this problem. The hero of our story is this really interesting quantum material called hafnium pentatelluride. Scientists found that, under just the right conditions, it didn't just survive being hit with radiation, it seemed to thrive on it. It did something nobody thought was even possible. What they found was a totally new state of matter, the excitonic liquid. So this is a quantum phase where the material, instead of getting destroyed, actually captures the energy from radiation. It then transforms it into this sea of energized particles called excitons. You can just think of an exciton as a tiny temporary packet of energy. To really get it, picture a solar panel that, instead of being shattered by a meteor shower, actually uses the energy from the impacts to charge itself up and instantly heal any damage. That's basically what this material does with radiation.
Okay, so how on earth does it actually work? Well, the whole process can be broken down into 4 key steps, or pillars, that turn this destructive force into clean, usable power.
First, the material transduces. That's just a fancy word for converts the raw radiation energy into those little energy packets, the excitons. Then it stabilizes itself, healing any potential damage and protecting the energy. Next, it extracts that stored energy as electricity. And finally, a special kind of circuit and architecture puts that power to work. Let's start with the most incredible part of this.
This is that stabilization pillar, and it's really the secret sauce here. The material's quantum structure is so incredibly resilient that it basically heals itself faster than the radiation can even damage it. It just shrugs off impacts that would absolutely destroy conventional electronics, all while keeping the energy it just absorbed safe and sound.
And when you look at the numbers, the difference is just staggering. It's not even a fair fight. After a huge dose of radiation, I'm talking enough to turn a standard silicon chip into a useless paperweight, the excitonic liquid is still chugging along at over 85% efficiency. Those conventional materials, they're toast. They drop below 10%. The performance gap is just immense.
Okay, so the material is tough. It captures the energy, but how do we actually use that energy? Well, those excitons we talked about, they act like a tiny rechargeable battery. They hold on to their charge for a relatively long time. Then, using these specialized interfaces made of graphene, we can tap into that stored energy and pull it out as electricity that we can use.
But how much power are we really talking about here? Well, a single radiation event can store up to 50 microjoules per square centimeter. Now, that might not sound like a lot, but believe me, it's more than enough to run an ultra-low-power AI chip for hours, all from a burst of energy that should have killed it.
So you can see this is way more than just a cool experiment in a lab. This technology unlocks a future where our most advanced electronics can power themselves in the absolute most hostile environments you can possibly imagine.
This timeline really puts the whole story into perspective, doesn't it? We go from the 1950s, when radiation was just this massive problem causing our first satellites to fail, all the way to 2026, with the discovery of a solution, and the projections are even more exciting.
We could be seeing the very first self-charging deep space probes by 2035, kicking off a brand new era.
So what does that era look like? Imagine deep space probes heading to Jupiter, or even further, that never run out of power. Their span is only limited by their physical parts wearing out. Think about self-sufficient AI on those probes, thinking and navigating all on its own. Or, right here on Earth, picture sensors inside nuclear reactors that are literally powered by the very radiation they're designed to monitor. It's a game changer.
So where does all this leave us? When you take a step back, this discovery is about so much more than just better spacecraft or tougher electronics. It really changes our entire perspective.
For almost 100 years, we've been fighting a war against radiation, treating it like an enemy we had to defend against. This technology completely shifts that relationship. It's not a battle anymore, it's a partnership. We're moving from a state of defense to one of symbiosis, where we can actually work with a fundamental force of the universe instead of just hiding from it.
And that leaves us with one last, truly fascinating question to chew on. If we can engineer a material to do this, is it possible that nature got there first? Could there be biological systems out there, maybe even here on Earth, that have evolved similar ways to not just survive radiation, but to actually thrive on it? It's a thought that opens up a whole new universe of possibilities, isn't it?